Okay, hello once again. So now we have a new video. So it's all about still balancing redox reactions, but this time we will be using a different method. So the previous videos were using half reaction method. For this video, I'll be focusing on another method, which is the oxidation numbers method. In this method, we'll be using the oxidation numbers of the different elements to be able to balance the redox reaction. But before we go to the real or the actual balancing, what I'm going to do is, of course, let's do a quick recap. Let's just do a quick recap of what redox is and what are the different rules involving oxidation numbers. There's a separate video for oxidation numbers alone. You might want to check it out. But for today's video, I'm gonna breeze through them and of course lead you toward solving two examples using the oxidation numbers method. So before anything else, what is redox again? So let's go back and okay, that doesn't want to go. Let's go. Okay. So redox, we know redox is actually a short for reduction oxidation. There are two processes in this cool big process, which is reduction and oxidation. So when you say oxidation, this is the loss of electrons or increase in the oxidation state, meaning the electronegativity decreases and there is a positive change in the oxidation number of the element because it loses its electrons. So definitely the net oxidation number will be positive. Whereas for reduction, this is the gain of electrons, meaning that there is an increase in the electronegativity, but definitely a decrease in the oxidation state. So of course, when a substance, an ion, or a compound gains electrons, it becomes more negative, thus the decrease in the oxidation state. Now, if you're kind of confused regarding what oxidation is and reduction is, there's a mnemonic. It's called oil rig. So always remember that in oil, that's oxidation is loss, and then in rig, that is reduction is gain. When we talk about losses and gains in redox, that will be, of course, the losses and gains of electrons. Again, in oil, that's oxidation is loss, and reduction is gain. Okay. I hope we begin to get used to what oxidation and reduction is. And of course, before we go to the actual problem solving, let's go back to the different oxidation number rules. There are actually 7, if I remember in the previous video, but this is now in summary form. So for an element standing by itself or it's alone in the reaction, the element has an oxidation number of 0, regardless of the number of atoms it has or the subscript it has. Always, if it's a standalone element in a reaction, it always gets a 0 oxidation number. Now for group 1A and group 2A. So group 1A, these are both the metals you see in the periodic table. So group 1A always has positive 1 and group 2A always have negative 1. If you want to know the different elements, here they are. So that's 1A and we have 2A. These are the metals. Except, of course, for hydrogen. Hydrogen is an exemption. Now, for halogens, usually they take the oxidation number of negative 1, but they are positive when combined with oxygen. So what are the different halogens? We have fluorine, chlorine, bromine, iodine, astatine, and that's a new one, tennessine. If you like to check TS, that's tennessine. So these are usually taking a negative 1 oxidation number unless they are paired with oxygen. Okay, so other rules that we need to know. For a monoatomic ion, it takes the ionic charge of that element. So we have 3 common monoatomic ions. We have hydrogen. Hydrogen is always positive 1 with non-metals and negative 1 when it's combined with metals. We also have oxygen. Oxygen is always negative 2 except when it's in a peroxide or in oxalates. So, but of course for redox, most of the time, you even saw this in the half reaction method that hydrogen and oxygen are the common ones. So usually they take the following oxidation numbers most of the time. And of course, we have fluorine. Fluorine is always -1. We saw from the previous slide that fluorine is a halogen, and normally it has a -1 oxidation number. Now, for polyatomic ions, the sum of oxidation number for neutral compounds in half reaction method, it was you were already introduced in compounds having net ionic charges. Now, for a neutral compound, the net ionic charge is always 0. And of course, for a polyatomic ion, you just have to take the ionic charge. These are the summary of the different rules in the use of oxidation numbers. It's very nice to keep them handy because you will be using them most of the time when you're using this method. So what is the method? How do we do the balancing using this oxidation numbers method? So there are actually 7 steps, 5 at the minimum because I just split um, steps 5, 6, 7. So the first step is actually identify the oxidation number of every atom. You identify what atoms are there in the reaction and then get the oxidation numbers. And then upon step number 2, after determining the oxidation numbers, what you need to do is look for the oxidation number, the change, comparing the reactant part and the product part. Because definitely in a redox reaction, some of the elements would change your oxidation numbers. Third step, this is actually the important one. Make the total increase in oxidation number equal to the total decrease in oxidation number. You have to equalize or you have to balance them out initially at this stage. The technique is actually to get that magic number, or it's actually a multiple, that magic number which you would be multiplying to the needed elements that were changed during the process. So definitely an element will be oxidized and another element will be reduced. And then after getting that, after equalizing it, you have to get that factor, and you will use this as coefficients in front of the formulas containing those atoms that change. So you're actually identifying a certain number, a coefficient, which you will be placing in front of the elements which need to be adjusted. And then, of course, we push through with balancing. In balancing, there's actually a hierarchy. When I say hierarchy, this have to go first. So you first have to balance non-hydrogen, non-oxygen, all other elements except hydrogen, oxygen. And then you balance oxygen, and then you balance hydrogen. And afterwards, when you really can't, for example, you come across a problem wherein there is lacking oxygen or lacking hydrogen, then you have to employ the step from half reaction method wherein you're adding water when there is a deficiency in oxygen, and you add hydrogen ions when there is a deficiency in hydrogen. But this is not always. It's just that, for example, at the end of balancing, you still can't balance it. I mean, you get to like a dead end. Hydrogen and oxygen do not balance. Then you have to add oxygen for water for oxygen, and hydrogen ions for hydrogen. Okay, I guess we're done with the steps. Maybe we can now go to straight to solving some examples. I have the 2 examples for this video. There will be other videos wherein they're very problem specific, just to give you more examples for the said topic. But for this video, just not to make it really long, I'll be doing 2 problems, and hopefully you get a grasp of what oxidation number method is. Okay, let's have the first example. My first example is a combination of nitric acid and arsenous acid yielding nitric oxide, arsenic acid, and water. Water here is a byproduct. So if we follow the steps, let's look at the steps again. First step, identify the oxidation numbers, look for the one that changed, equalize, get a factor, and then balance. Those are just really quick, simple steps. So first from the list is listing the different elements in this reaction, and then finding the oxidation numbers. So we have hydrogen, we have nitrogen, we have oxygen, we have arsenic. Okay, are there other elements? Let's try again. That's hydrogen, nitrogen, oxygen, arsenic. And I'll also do that in the first product side. Of course, there's also hydrogen. We have nitrogen, which is this one. We have oxygen. We have arsenic. Okay, identified. There's hydrogen and that's oxygen. Okay. And then the step says that you have to identify the oxidation numbers. We have to go back now to the different rules that you're using in the oxidation numbers method. So we know that hydrogen always takes a positive one. So this is also positive one. And we also know that oxygen has a negative 2 oxidation number. Why am I doing this? In most or 90% of redox reactions, you always see hydrogen and oxygen. And most of the time, they take these oxidation numbers. They still follow the rules. That's why you always look for something that is known before going to something that you're not really familiar with, like nitrogen and arsenic. You may find a table that shows you the different oxidation numbers, but if you can already solve it manually and these are just small numbers, then do so. Just look for something known or remember something known. Like in our case, hydrogen and oxygen are just like staples already. You know them already. So let's first look for what nitrogen's oxidation number is. So that's HNO3. So the technique here, you don't see any charges on the different elements or different compounds. You don't see something negative or positive on top of every compound. So it means that these are not charged ions. These are not charged polyatomic ions, but they would take a neutral charge or neutral oxidation number. So for HNO3, we know that there are 3 atoms of oxygen times negative 2, which we already identified. So that's a negative 6. We also are aware of hydrogen, which is positive 1. Getting the net of the two, we have negative 5. So you think of a number that would offset negative 5 or make the whole sum of the oxidation numbers of nitric acid 0. So negative 5, of course, it follows that nitrogen has positive 5. So both of them, when added together, will have 0. So we can assume here that nitrogen has positive 5. Okay, what about arsenic? Arsenic in H3ASO3, or this is arsenous acid. So let's have it here. Let's put it here. H3ASO3. You know that that's 3 times negative 2. And this is positive 3. So that's equal to negative 6 plus 3. That's a negative 3. Therefore, arsenic will take a positive 3 oxidation number. Okay. So again, how did I do that? And what was the concept behind? You don't see anything like a charge on top of the compounds, meaning at this point, the compounds are actually neutral. So the sum of the oxidation numbers per compound should be equal to 0. Okay, let's just erase this. Should you have questions, probably you can just list them now and then maybe we'll talk about them when we have our sync class. But for now, let's just go through the solution so that you can follow it in the event that you need to use oxidation numbers for different exercises. Okay, let's just erase this. Okay, now we're done with the reactant side. Let's now go to the product side. Okay, I can't assume that we have to take in the same because the forms of a nitrogen and arsenic are different on the product side. Like in this, on this side, nitrogen now is paired with oxygen for nitric oxide. So we know that oxygen always has negative 2, therefore nitrogen has positive 2. And let's go here for arsenic acid. 4 times negative 2, that is negative 8 plus 3, that's a negative 5, which means arsenic takes a positive 5 oxidation number for the product side. That's actually just step number 1. Step number 2, you have to identify which change. So let's see, which change? Well, we can see it very clearly that nitrogen changed and arsenic changed. When we say change, there's actually a change in oxidation number from the product to the reactant side. So let's list them. We have nitrogen, which changed from 5 to positive 2. And we have arsenic, which changed from positive 3 to positive 5. You can actually see it right away. From positive 5 to positive 2, meaning what happened? It gained electrons because it became a little negative, or the number decreased. So there's actually a negative 3 change here. There's a negative 3 change in oxidation number. Okay, that's positive 5 minus 3, that's a positive 2. But on arsenic's side, that's a positive 3 to positive 5, meaning there's an increase in the positive, or there it lost electrons, okay? Because what happened to the element, it became more positive. So going back to our oil rig definition, oxidation is lost. So this is now, because what happened here, positive 5 plus positive 2. So this is positive 3 plus positive 5. This is our oxidation. This is our reduction. Why is that? Okay, oxidation is lost, meaning there is a positive change. It decreases electronegativity. So this is the oxidation stage. This is the reduction. But of course, when it comes to agents, arsenic is the reducing agent and nitrogen is the oxidizing agent. Because what made it oxidize? It's nitrogen. What made it reduce? It's arsenic. So take note of that. Now you have you've already seen the net change in oxidation number. Now you think of a multiple that is common to both, and that's, we know very well, that's 6. So you have to multiply this one, the nitrogen side, to 2, and the arsenic side to 3. Don't care about the sign yet because you already identified which is which. So meaning you have to balance. So 2 times 3, that's 6, and 3 times 2, that's also 6. We're actually talking about a movement of 6 electrons. We need to balance them. We need to equalize them. So look at the rule again. It says, knowing the factors that you need to equalize, you would put those factors in front of the elements as coefficients. So let's just change my ink color. Okay, just for like discussion purposes. It says there, for every nitrogen that we see, we will have to put a 2 coefficient. So let's put 2 here. And then look for another set of the one with the nitrogen. And then with arsenic, you have to put 3. Okay, there you go. And then try to balance it. Try to balance it. In this example, of course, this is just a start-up example for the topic. Let's see if it's balanced. And when we're balancing, the hierarchy again is non-oxygen, non-hydrogen, oxygen, and then hydrogen. So let's focus first on the non-oxygen, non-hydrogen, which is nitrogen is the first one. So how many nitrogens do we have here? That's 2. And then on the product side, we have 2. Okay, that's 2 and 2. Let's check. Okay, what about arsenic? That's a non-hydrogen, non-oxygen. For arsenic, we have 3. We also have 3 arsenic here. Okay, let's check. It's balanced. Now we balance oxygen. So oxygen, let's count the number of oxygen that we see on both sides. So that's 3 times 2, that's 6, plus 3 times 3, 9. We have 15 oxygen atoms. And then here we have 2. And then 4 times 3, that's 12, plus 2, that's 14, that's 15. So it's balanced as well. And finally, for hydrogen, how many hydrogen atoms do we see? That's 2, plus 3 times 3, that's 9. And then that's 3, that's 11 on this side. And that's 2 Oops, did I miss something? That's 9. Yep, okay. And then here, sorry, here for hydrogen, that's 9 plus 10, 11. So 11. There you go. So your final answer for a balanced redox reaction is this one. Let's rewrite that. That's 2HNO3 plus 3H3 ASO3 yields 2NO plus 3H3ASO4 plus H2O. That's your final answer. This is actually your final answer. I just rewrote it just for, to highlight the answer. Okay, probably let's have another one. So we'll have a longer one, and so that we can look for, because in that example, we really didn't do a lot like balance oxygen or hydrogen. So probably let's have another one before we end the video. So we have here FeI3 plus HClO4 plus H2SO4 yields HIO plus HCl plus Fe2SO4 3. So again, I'm doing my steps as tabular, listing the items or listing the elements tabular in a tabular form. You may also, what you can do is you can also put them on top of the elements. Like we know I I I3. Iodine is a halogen, so this is always -1. So 3 times -1, that's a +3 for iron. And then for HClO4, we know that this is -2. And hydrogen is +1. Therefore, that's 4 times -2. That's a -8 plus 1. That's a -7. So Cl is +7. That's the reason why I don't use this for my discussion, because it's gonna cramp up, on top of the action. But I'm just showing you an alternative on how you can do it. Now, this is a polyatomic ion. For SO4, I'm using it as 1 unit. So this is a sulfate. I'll probably provide you a table. And when a sulfate, it has a -2 oxidation number. So if this is -2, so this is also +1. It also follows that it's neutral, because 2 times +1, that's 2, and then only 1 sulfate here, that's a -2, that's still 0. Now for HIO, so we know that this is -2, hydrogen is +1, therefore we also know that here iodine is +1. So what about HCl? We know that H is +1, therefore Cl is -1. SO4, we know that's -2 times 3, that's -6, divided by 2, that's 3. So this is +3 still. You can do it this way. I said when I started with the presentation, when I started solving it, that there is no absolute way on how to list the elements and their oxidation numbers. You may wish to use this, that's fine. Maybe you want to save space, that's fine with me. But this is another way in assigning oxidation numbers to the different elements. The problem with this method is, of course, if you get confused, or probably when your little handwriting gets overlapped, you might not, you might have some errors, but still this works, okay? This works. So which change oxidation number? We're done with step 1. Now step 2 is to identify which change. Did iron change? No. Did iodine change? Yes. Yes, I believe so. Did iodine change? Yes, it's from -1 to +1. So let's list that. The first change is iodine. So it's from -1 to +1. Hydrogen, of course, that didn't change. But chlorine changed, because I believe chlorine here is -1. So chlorine here is +7. So let's take chlorine and let's fix that. That didn't go too well. Okay. Get my tool again. Okay, let's get chlorine. Chlorine. Okay. So chlorine is from product reactant side, that's plus 7, and in the product side, chlorine is a negative 1. Okay, so those are the changes. Hydrogen did not change. Sulfate retains its negative 2 oxidation number. So let's identify the change from negative 1 to positive 1. So what is the change? So that's actually a positive 2, right? Because from positive 2 minus 1 plus 2 minus 1, that's a positive 1. What about plus 7 to negative 1? That's actually a negative 8, because negative 8 plus 7, that's a minus 1. Therefore, looking at the two factors, now we have to equalize them. So equalize them, probably the common factor here is 2. So 8 divided by 2, that's a 4. So we multiply this part of the reaction by 4. So the equalizing factor is 4. So anything with iodine, we put 4. And of course, for chlorine, you just multiply 1. Okay, let's first identify which part was oxidized and which was reduced. So in oxidation, it becomes more positive. Oxidation is loss. So anything that became more positive. So this is the oxy side, and this is the reduction side. Cl, or chlorine, is your oxidizing agent, and iodine is your reducing agent. Let's just rewrite the equation so that we can place our coefficients better. Let's put a little space. So we might, okay, ClO4 plus H2SO4 yields HIO plus HCl plus Fe2SO4, and 3 units of that. Okay, let's see. Again, we will be multiplying anything, a compound or an element with iodine in it with a factor of 4. So let's just have yellow again, probably. So 4, anything with iodine, we put 4. So let's put 4. And this also has 4. Oh, sorry, that's not iodine. Sorry. Okay. Oops. Okay. So here, let's put 4. And then that's it. Because for chlorine, you just have to multiply chlorine compounds with chlorine with 1. So let's not do that anymore. So let's try to balance it. So in balancing, again, the hierarchy is balance first, non-oxygen, non-hydrogen. So let's start with iron. That's 4 irons here. You only have 2 here. So let's put a 2 here. That's 4. And then iodine here is 4 times 3. That's 12. So let's first change this now. From previously 4, we change it to 12. Okay. Okay, what else? We have chlorine. Chlorine is 1. Chlorine is 1 here. So what about SO4? We have how many SO4s here? It's already 6, right? Because 3, oops. We have 3 times 2, that's 6. So probably let's put a 6 here. Okay, now that it's doing that. Okay, let's put a 6 here. Okay. Now that's balancing non-oxygen and non-hydrogen. Now let's go to oxygen. So in oxygen, well, it's quite obvious here. It becomes 12 right away because of the coefficient 12. But we only have 4 here on this side. So we have to multiply this by 3. And knowing that, because that affected chlorine, you have to put 3 here as well. And let's see if hydrogen fits and if it's balanced. How many hydrogens do we have? 3. And then 12, that's 15. We have 12, 13, 14, 15. And let's check if it's the whole thing is balanced. We have 4 iron, 4 here. Iodine has 4 times 3, that's 12. We have 12 I's here. Chlorine has 3 chlorine. Sulfate, 6SO4. So that's SO4, 3 times 2, that's 6. Oxygen, that's 12. And finally, hydrogen, that's 3 plus 12, 15. That's 12 plus 3, 15. So this is our final answer. So this is the final balance equation. We did not experience a compound or a reaction wherein we had to add oxygen and we had to add water for oxygen and hydrogen ions for deficiency in hydrogen. You can see those examples in our other videos regarding balancing redox reactions. So this is how you do your oxidation numbers method. It's up to you if you want to use this method or the half reaction method, where if you find yourself more comfortable using this, then use this. If you feel that you are more comfortable using the half reaction method, that is also not a problem. So for other videos, please keep on subscribing. Please keep on sharing the videos as are for you guys, so that you can, of course, go back to it and review every now and then what we're taking in our different classes. So that will be my video for today. Please don't forget always to subscribe and, of course, click that bell so that when there's a new video, you will be notified. Thank you so much. And, of course, till our next video. Thank you.